Hello, this is Singtek Lee, and this is my Physics 2212 Lab 4 report. The purpose of this lab is to predict and measure the behavior of circuits containing resistors and capacitors using principles of energy and current conservations. So the fundamental principles I'll be using is the energy conservation, which we could use the loop and node rule, and the principle of current conservations and Ohm's law, which means potential difference equals current times resistance. The results of this lab will be thoroughly discussed in the lab report, but it is found that the assumption was equal to the prediction at most cases. For the first assumption I made for this lab is the steady state conditions, which means all transients are non-existent, and this ensures consistent measurements over time. And I neglected the resistance of the wires in the circuits. So the circuit is the sole system for this lab, and everything else except the circuit is the surroundings. This is experiment model 1, and it's a circuit containing two 1.5 volt batteries and two resistors, each 47 and 100 ohms, and 2 ammeters. So the first analysis I'll be talking about is current conservation. So I predicted that the first current and the second current will be equal, and I tried to prove it by using a calculation using Ohm's law and loop rule, and I calculated the current to be 0.02 amperes, and by using the model simulation online, it was indeed 0.02 amperes displayed in the ammeters. So I resulted that the first current and the second current is same. And I also did an additional case study by substituting one ammeter to one voltmeter. And the voltmeter made an open circuit, and this resulted to no currents flow in the circuit. So the voltmeter was to be measured to be 3 volts, and the ammeter displayed 0 amperes. But if we haven't excluded the ammeter and just included the voltmeter and the wires, the ammeter results doesn't change due to the high resistance of the voltmeter, since it ensures drawing negligible current. So the ammeter would still be displaying 2 amperes, 0.2 amperes. And this also I'll be doing an analysis about loop rule. And according to the loop rule, the potential difference for the round-up circuit should be 0 volts. And I did a calculation of all of these locations in the circuits. So starting from A to H and summing up all of these potential difference resulted to 0 volts. So this is a graph plot of explaining the potential difference between when it passes through different locations starting from A to H. So as you can see, in the power source from A to B, the potential difference increases to 3 volts, but after we pass through the 100 ohm resistor, it decreases and finally reaches 0 volts. And we did another case study when we added an ammeter parallel to the 100 ohm resistor, and the current increased to 0.06 amperes. The reason is since the flowing current splits into two, the resistor and the ammeter, the resistance decreases. So in result, the current increases. And I calculated the resistance for the two resistors and the wire and the ammeters using Ohm's law. And we found out that wire and the ammeter was 0 ohms. And this is model 2, which we located the battery and the capacitor and the light bulb in series. So when these three devices were connected in series, the light dims gradually. And when we exclude the battery and just connect the capacitor and the light bulb, the light also dims gradually, since the capacitor's charges were sent to the light bulb. And this discharge time varies by 10.3 seconds for the 10 ohm light bulb and 20.5 seconds for the 20 ohm light bulb. And lastly, I made a time dependence analysis of this model 2. And we plotted a graph of ln delta V over delta V initial versus time, and the slope will be calculated by using -1 over RC, which was calculated to be -0.1667. And the RC value here is called the time constant, which is the time at which the voltage difference has dropped to 1 over E of its original value, and the RC value for these values was supposed to be 6 seconds. But the measured slope by using the model simulator, I got -0.1735, and the ln V over V initial at 20 seconds was to be -3.47. So by using these values, the picture below is the graph I plotted. So the measurement for Model 2 time dependency experiment doesn't exactly match with the pre-done calculations. The reason is that I did not stop the time watch at exactly 20 seconds. So this can be considered as human error. and there could also be software limitations for the model as well. So for the first what if questions, I answered that since the real ammeter has internal resistance, this could lead to measurement errors which would be different with the expected results. And for the second question, I answered in reality, the internal resistance would cause the battery charge a slight delay, which would lead to longer time to charge than expected. Thank you.